Hello, my name is Tom Hebb. I'm a security engineer on Meta Red Team X, and we do external vulnerability analysis of various products. You can see some of our blog posts and external research at this URL here. And today I'm going to be continuing the video series I started with part 1 on how to analyze firmware. So in that last part, we talked about all the steps up to and including getting a copy of a firmware file for some device you want to analyze. So at this point, you know what device you're analyzing the firmware for, what you're targeting. You have some firmware file, and you're trying to figure out what to do with it. So the first thing you might do, which a lot of people will do, is just try and figure out what kind of file it is. On Linux, you can use the file utility for this. And sometimes you'll get lucky. The example we had last time of that Wi-Fi firmware, m3.bin, it turns out it's just a normal ELF executable, the same as any other executable on Linux. You can see it's a little strange. It says it's for a 386, which I'm pretty sure is not right because no one uses x86 in firmware, to put it politely. And also the name of this file, m3.bin, indicates pretty strongly that it's designed to run on an ARM Cortex-M3 core, which is ARM architecture, not an Intel 386. But that's kind of emblematic of the types of things you'll see in firmware. You'll see something that's like mostly conformant to some specification, but has its own little quirks. So apart from dealing with those little quirks, in general, a file like this you can just treat as if it's a normal ELF executable and use all the existing tools to parse that and get out the executable code inside. But more often than not, you're not going to have this. Instead, you're often going to see this, which is just a file that cannot be identified. So what this data means as the output of file is that none of its internal database of different file types, ELF, PE, PNG, JPEG, all of the common file formats we're all familiar with match this file. So this file just has something it doesn't know about. And additionally, we know that this file is not just readable ASCII text, like a device tree maybe, because it just has data. It doesn't say text. So in general, something like this is going to be pretty hard to just open with standard tools and figure out what's going on. The one standard tool you might think of is a hex editor. So a hex editor just shows the raw bytes of any file, and it's tempting to just open a file in a hex editor and stare at it real hard and try to figure out what's going on. In my experience, that generally doesn't get you very far. And the reason for that is that there's just so much complexity and nested structures and length prefixed things in binary formats that are just not easy for our brain to understand when we're just staring at the bytes. You really need some program to parse any significant quantity of data at all as binary, even if it's pretty simple data under the hood. And so you start looking for tools that are better at this. And you might come across these tools that are kind of pattern matching tools. File is one of these tools. It goes and looks for recognized signatures. And then there are some more that you might have heard of that go deeper. There's a tool called strings, which shows you all of the sequences of ASCII characters that exist in a file, everything it can find. And because code usually includes some kind of user-facing message, even if it's just a log message, that can help you sort of see what's in a file. Binwalk is a step above that. What it basically does is it's like file, but instead of just checking the fixed offsets at the beginning and end, it goes through the file byte by byte, and at each byte looks for a JPEG header, a PNG header, all that stuff. And so Binwalk is like, if you have a whole file system image with a bunch of uncompressed, unencrypted files on there, Binwalk can kind of show you, what files exist where. But it's really just a pattern matcher. It doesn't understand the enclosing format. It just looks for those sequences of bytes that it recognizes and throws everything else away. And so tools like this, they're better than nothing, but I never use them for analyzing firmware. I only ever use them to sort of get a high-level sense of what a firmware file might be. But once you have that high-level sense, what you really, really want, and what the gold standard is a parser. You want something that actually knows what's going on in that file format. And that's, for example, what standard ELF tooling is, objdump, readelf. These things are parsers for ELF files. And they're readily available because ELF is a very widely known and used format. Unfortunately, most firmware formats that you find are going to be completely custom. And you might get lucky and find a tool someone's written to parse them. But in many cases, you'll have to write your own. And if you've ever written a C program or a Python program that tries to just like parse a file, you know it's pretty frustrating. Like handling all the offsets in a clean way, like adapting when you don't really know what's there and just want to scope things out is really hard because you need to write a bunch of boilerplate code and refactor all your code every time something changes or gets nested a level deeper, or you realize something isn't what you thought it was. And it's just in general like pretty janky. It has potentially vulnerabilities even if you're using a memory unsafe language like C to parse this file. And I just find it very, very cumbersome. And so I have a tool that I prefer for creating parsers in a clean and efficient way. That tool is called Struct. That website might lead you to believe that it isn't good for reverse engineering. Everything on here talks about just creating parsers for your software project. But I think this from page really undersells it, and specifically undersells this link right up here, the web IDE. So when you click that, this is what you see. And this is really what you want as a reverse engineer out of Struct. It has a lot of other stuff. It has libraries you can use from all sorts of languages. But this web IDE is what makes it so, so useful. Basically, this is a way to write a declarative specification of the contents of a binary file. So it has the hex editor you're used to, but it's just one of all these panes. So you see the hex editor, but you also see your declaration in the left here. And then the hex editor is highlighted based on the fields that it parses out for you automatically based on your specification. And then down in the lower left, you can see a hierarchical view of all of those values with appropriate type information. You can have enumerations, all sorts of stuff. It has a good user guide. And this is so far the best tool that I found for doing this step of the reversing. So for figuring out unknown binary format. I kind of think of this as like a Ghidra for binary formats, for data formats. There are other tools like this. If you've heard of 010 editor, for example, that's a closed source hex editor that has very similar features. But I like Struct more because it's open source. It has a web IDE. You can use it from anywhere. And it's very, very easy to share these specifications and just let anyone use them. So I will show how this actually works in the next video, so make sure to watch that. For now, just know that Struct lets you sort of iteratively go through from a file format that's completely unknown to you into something you understand. And you can just gradually sort of look at the hex, figure out what's happening, add in new things to your specification without having to deal with a bunch of C or Python boilerplate. So what exactly is it that you're trying to find with a tool like Struct? There are two really, really key things that you need out of this extract phase before you go on to the next analyze phase and load this up into something like Ghidra. The first is the instruction set. So you need to know, or rather, I guess I should say the first is actually the code itself. You need the binary code, and you need it in sort of a pure form. You don't want any headers or data wrapping it because that's going to mess up the alignment and the offsets. You want to know exactly what parts of this whole firmware file just contain binary code. And part of knowing that is knowing what architecture that code is for. So in some cases, for example, if your file is named M3, you can be pretty sure that's ARM architecture. Cortex M3 is an ARM chip. And so you can get hints from there. You can get hints from datasheets, from reference manuals. And And in fact, the files themselves generally won't even bother to say what architecture it is because that's part of the chip itself. The thing that the files do have and that you can't really find anywhere else is information about the memory map. So you're probably familiar that when you run a program on Windows or Linux, it will load the program from a binary file on disk into RAM and then start executing it from there. And it will load it at some offset in RAM, and all of the different sections of an ELF file can get loaded at different places with different protection characteristics and all that kind of stuff. The same exact thing is true for firmware, but you don't have the luxury of those known ELF headers telling you where everything gets loaded. So you might have a big chunk of code, but you need to know what RAM that gets loaded in, and specifically what address that RAM starts at, because most of this code isn't position independent. It's going to reference other things, other pieces of code, static variables and constants that are that need to be placed correctly when you go and reverse it, or else you're not going to be able to tell what's happening. Over here on the right are some screenshots from Ghidra and Binary Ninja showing how you can configure a memory map. You can see each of these sections has a start address. Many of these are mapped to a file, so you have parts of your actual firmware file on disk backing these regions. And then they also all have protection attributes here. So this is saying, can this be read? Can this be written? Can it be executed? In this case, this is for some firmware. So what I've done is I found the code that maps into RAM. I found the address at which it's mapped. And then I've added that as a section in Ghidra mapped to the file so that it can place it at the correct location. And because this is just the executable code, I've marked it as readable and executable, but not writable. You might ask, if this is in RAM, shouldn't you mark it as writable? Can't it be written? And that's true. Strictly, yes, it should be marked writable. But I can use the knowledge that this code was generated by a modern compiler and assume it's not going to modify itself. Like, self-modifying code doesn't get emitted by modern compilers. And so by unchecking this writable box, I can enable some extra optimizations in Ghidra that aren't possible if it thinks that this memory will ever be written. Then I've mapped other sections of the file as data sections, and those are readable and writable because they get modified while the program runs. And then I really want to highlight this fourth entry, peripherals. Peripherals might be unfamiliar to you if you haven't ever worked with microcontrollers or embedded systems. And the reason for that is that on Windows or Linux, every memory address is RAM, or at least the OS makes it look like that. If you write to some address that isn't mapped, the OS will go behind the scenes, page fault, find a free page of RAM for you, and just give it to you. And so it behaves like RAM. You write a value to one address, you read that address later, you get that value back. And that's all of the memory in your Windows or Linux program for the most part. When you want to do something, when you want to print a character to the screen or draw something or make a sound, you make a syscall. So you call into the operating system and you say, hey, Linux kernel, I want to do something, and then the Linux kernel goes and does its magic. But when you're running bare metal code, like most firmware is, when there's no operating system, there are also no syscalls. There's nothing to call to say, hey, I want to write a character out the serial port, for example. So how do you do it? In most modern chips, it's actually done just using memory, reads and writes just like anything else. And so this brings us to what's called memory mapped I/O. This is a fixture of basically any modern chip, from the tiniest little microcontroller up to a full desktop CPU. And the kernel, or whatever's running directly on the hardware, will be using this to perform actions. So here's a real function I found while reversing a piece of firmware. And if you expect all of the memory to be RAM, this is nonsensical, because what it's doing is, on the second line here, it's writing some static value, saving some static value to this address in memory. The DAT indicates that. So 10007000, that's a fixed address in memory, hard-coded, and it's just shoving that value there. It's doing a plain memory write. Then it's waiting hex 28 microseconds, and it is reading back that exact same value. And I've clipped it out, but it does make a decision based on this uvar1, based on the result of that read. So if this were RAM, it wouldn't make any sense at all, because you would know what it was going to read. It wouldn't need to wait. It wouldn't need to do anything. It would just be able to take this value and shove it right down there directly. And the reason this doesn't make sense is because it's not RAM. This is writing to what's called a register, and a register is what makes up all of these memory-mapped I/O or peripheral regions. So every bit in the register has some meaning to the hardware. And when you write to a bit, you're telling the hardware, hey, enable this interrupt maybe, or like, save this, these 8 bytes of the register as an entry in the queue that's going to go out the serial port, or any number of things. Or like if you have a board with I/O pins, like a Raspberry Pi, there's a register that says, here's the state of all these pins, and you write to it and the state changes. It turns a pin on or turns the pin off. And that is what this volatile check mark and this peripherals region indicate. So the peripherals region, it starts at a nice round number. That's very common for peripherals. And then I've put it all in one big chunk, but this is actually going to be lots and lots of peripherals all lined up in a row. So for example, the flash controller, flash storage controller is usually a set of registers. The GPU on a mobile chipset is a set of registers. The serial port is a set of registers. The GPIO, power buttons, LEDs, things like that, another set of registers. Every single thing the chip knows how to do, sort of in the real world, is exposed through some set of registers in the memory mapped I/O. And the reason I've marked this volatile is because when you analyze code in Ghidra, it will by default assume that all memory is RAM, that when you write something, the same thing will be read back, and it will do optimizations to the decompilation to make it simpler based on that assumption. So if I didn't have this marked as volatile, Ghidra might just completely ignore this delay, because it would say, or at least it wouldn't order these in this way. It might just say delay, and then uvar1 equals this fixed value, just like you would expect to be a valid optimization if this were RAM. So marking the peripherals as volatile is very important for that reason. That is the basics of static analysis for firmware that you find. And the demo in the next video will show you a real-world example of getting out code, finding all these segments and marking them. And then once you've done that, it's just like analyzing any binary in Ghidra. So I'm not going to go into the specifics of that, and I'll leave it there for static analysis. Let's talk a little bit about dynamic analysis. So dynamic analysis is like your GDB or debugger, figuring out what's actually happening as the system runs. And in many cases, this will go hand in hand with static analysis. So you'll have your program loaded up, you'll be looking at its disassembly, and you'll say, hey, I don't know which branch this code takes, if it goes, if this value is 1 or 0, and which of these functions that might be called to analyze. And so instead of tracing it all back in the code, I just want to see what happens in real life. So this, again, is very, very device specific, but I wanted to give some pointers at least. So if you just want to see what's happening, log messages from the firmware, for example, then there are a few things you can do. You can look at whatever bus is going between that device and the main chip. So for example, if you have a flash storage chip using eMMC, you can put a logic analyzer on those eMMC lines and see what data is flowing back and forth. That requires opening up your device, having physical access to the internals. Sometimes you don't have the equipment for that. And in those cases, you might look for things that are built into the kernel driver. Maybe there is existing debug functionality from the manufacturer that just needs to be turned on. And this is, again, where reading the kernel source can come in very helpful. There are various specifications called closed case debugging or something like that, which lets you get like serial output, log output from various bits of firmware. from your phone without having to open it up, just over a special mode of the USB port. You can look for stuff like that. And then you can get log messages, and you can say, OK, I know this log message is printed by this function I found in the disassembly, so I know that's getting called and when it's getting called. Then you might want to start sort of changing those code paths by sending the device different data to exploit a vulnerability you found, perhaps, or to make just more of the firmware run so you can see what it does and help with your static analysis. And so in that case, there are some more techniques you can use. Again, you can modify your kernel, modify the code you do have access to. If you have a rooted device, this is often very easy. If you don't, then you might need to find more bugs. And then in many cases, that's enough to just call some vendor-specific, manufacturing test function you found that was never supposed to be there, but it is, and calling that lets you, make the firmware do something bad, run code in the firmware, whatever your goal is. Sometimes you can trigger that from the kernel. And then if you want to do it physically, then most CPU cores, even firmware CPU cores, have interfaces like JTAG, which let you run hardware debuggers, and you can use tools like OpenOCD for that, for example. And then finally, you might actually want to change the firmware image itself. And if you want to change the firmware image itself, you have a few options. If you're very lucky and it's just loaded from the kernel at every boot, you can just change the file on disk, repack it, maybe write a tool to repack it, using all that stuff you discovered back in the extract phase, and then write it back to the chip. Just replace it on the file system, let it get loaded. But if it's internal to the chip, you might need to use something like one of those firmware update mechanisms I mentioned before, firmware upgrade protocols. And always when you're talking about modifying firmware, you have to be aware of any security measures that are there to prevent modification. Usually this is signing. So for example, bootloader firmware, pre-boot code on any modern phone will all be signed because it's establishing a chain of trust. So it starts at the very beginning with a public key that's burned into the chip itself, and it will only run code signed with that public key. And then that code will only run code signed with some other public key that it embeds. And eventually we get all the way up to the main operating system, each stage verifying the next stage. So usually that won't be encrypted. Sometimes it is, which is another hurdle. But even if it's not encrypted, changing it will invalidate the signature, and you won't be able to, you'll often have a brick device on your hands. For external devices like Wi-Fi cards, audio codecs, it's less likely for firmware to be signed, but it does happen. And so generally you're reversing in the extract phase, your extraction of the file will show you if there are any signature blobs, big sort of random looking pieces of data that might be cryptographic information used to verify the firmware. And in that case, you'll need to find a bug in the signature verification or just half the private key, which most people don't. But again, you can sometimes bypass this if you're willing to physically open up your device just for testing. Obviously, if you report a bug to us for bug bounty that requires you to open up a device and attach JTAG to some chip in order to run code, that's not going to be a valid bug because you're already sort of at the level where you can do anything you want if you have the device open up with test probes on it. But for research, it can be useful, and JTAG and SWD often let you bypass signing because you can just read and write the memory directly. You don't need to care about what's loading code into that memory. Cool, so that's dynamic analysis, and that brings us to the end of part 2. So stay tuned for part 3, where we will talk about how this looks in practice, and I'll be going through an actual demo of reverse engineering firmware on a real chip on the Oculus Quest 2.